Okay, and welcome to the problem-solving portion of the 1.2 video. I have 3 example problems that I'm going to go through, 2 of which require me to write some stuff down on paper, and the third one is actually just something that I'm going to talk about. Not necessarily a problem that we have to solve, but it is an important skill that I want you to be exposed to. So, before we go any further, though, let me go ahead and show you once again what the learning objective was for this topic. So, we are needing to be able to explain the quantitative relationship between the mass spectrum of an element and the masses of the element's isotope. Essentially, what that means is we need to be able to explain when we see the mass spectrum of an element, which is like the data from a mass spectrometer, how does that relate? Okay, what's the relationship between the data and the actual masses of an element's isotopes? And we're actually going to go a couple steps further than that, and you'll see that in just a minute. Okay, so let me fast forward on the slides here quite a bit. I'm going to go all the way to the end. Here we go. So like I said, I've got 3 example problems, and one of them is actually one of the problems that I have assigned to you in the homework for this topic. So I guess you have one less problem that you have to do by yourself. This is from chapter 3, number 39. So it tells us that we have an element that consists of 1.4% of an isotope with mass 203.973 U. This unit, by the way, is the atomic mass unit. I referenced that way back here when I was talking about subatomic particles. Essentially, protons and neutrons each have a mass of 1 atomic mass unit, roughly. So here what this means is that this isotope that only has 1.4% presence in the sample has a mass of this many atomic mass units. Okay, just keep in mind that those atomic mass units of protons and neutrons are approximately 1 each, and so that is why there is a little bit of deviation here from a whole number. Okay, and you see that crop up in all of the masses. It's just slightly less than a whole number, right? This is 203.97, almost 204. Okay, so it gives us the data here for 4 different isotopes of an element with different masses. What I'm going to do is I'm going to write this data down in a table. Okay, and here's what the question is ultimately asking us. It wants us to calculate the average atomic mass based on this data and then use that to identify the element. Okay, so like I said, I'm going to take this data and I'm going to tabulate it on my piece of paper here, okay, just so it's a little bit easier to look at. Okay, so this was chapter 3, number 39. I'm going to make a table. I only need 2 columns because I only have 2 sorts of data. I have masses, or mass numbers, and I have percentages. Those percentages are referred to as relative abundances, or the relative abundance of different isotopes. Just to pull you back to the slides here for just a second, if we go back and look at this data here, that's essentially the y-axis on these 2 graphs, okay? This is the actual data that comes out of the mass spectrometer, okay? And so this is the ion beam intensity at the detector, okay? So like the more intensity, the more of that individual isotope. This is then translated into data that looks like this, okay? And this number of atoms is basically the same as relative abundance, okay? If these numbers add up to 100, which in this case they don't, I'm going to talk about that in just a minute, then you can actually use these numbers to just give you the percentages, okay? I'll talk a little bit more about that later. Anyways, to go back to the graph here, or to my table, we have 4 mass numbers and their 4 corresponding relative abundances. Okay, the mass numbers were 203.973. Once again, those were in units of atomic mass units, which they just used the letter U for. That isotope, or that mass number, had a percentage of 1.40%. You could put a little percent sign here. Okay, and then I'll just go ahead and fill in the rest of these. So 205.9745. That percentage was 24.10. The next one was 206.9759. That one had a percentage of 22.10%. And then the fourth and final isotope that was detected had a mass of 207.9766, and that one was the most abundant with a percentage of 52.40%. Okay, it is very important that your relative abundances add up to 100%. Okay, so if you are, for example, looking at a problem and you're rewriting the numbers down on your piece of paper, you may just want to double check that those numbers do add up to 100%. And in this case, they do. Okay, so this is some data that you may have pulled from a mass spectrometer. One thing that we can do right off the bat, okay, so those are the mass numbers, 203.97, so essentially 204, essentially 206, essentially 207, essentially 208. We can just go take a look at the periodic table, and we can take a look here and say, okay, what are some of the possibilities? Which elements could this be? Okay, I'll read those mass numbers off to you again. 204, 206, 207, and 208. Okay, so 204 to 208, those were the only possibilities. It can't be mercury. Okay, because if the average atomic mass is 200.59, those mass numbers, like, there's no way that if you average those mass numbers you're ever going to get 200, right? All those masses are bigger than 200. Same thing for bismuth on the other end. All of those mass numbers are less than 208.98. That leaves us with only 2 possibilities. Okay, TL, which I believe is thallium, and Pb, which is definitely lead. Okay, and these are the 2 average atomic masses for those 2 elements. So the problem asked us to calculate the average atomic mass and identify the element. We've already narrowed it down to 2 possibilities. Okay, so even if you say can't do this first part, just by looking at the mass numbers and sort of checking on the periodic table at looking at the possibilities, you can get yourself down to a 50-50 on this second part, right? But let's talk about how to actually calculate the average atomic mass. Okay, so the formula kind of goes like this, okay? And if you had me last year, you definitely saw this. I believe you've probably seen this if you've taken a year of chemistry before with any teacher, okay? The average atomic mass for an element is equal to, and this is like a generic formula, okay? It's equal to the sum, okay, that's like the symbol for sums, of the mass number times the relative abundance. Okay, so basically you take the mass number, you multiply it times the relative abundance, figure out what that is, do that for all 4, add them up, and that is going to be the average atomic mass for that isotope. Okay, this is called a weighted average calculation. It's the same type of calculation that you use to calculate your GPA. And essentially it's just doing some multiplying and adding, and that's it. Okay, so I will go ahead and write the whole thing out here for you just so you can see it. You can go ahead and put these things in parentheses if you want to. It's actually not necessary since multiplication does take precedence in the order of operations above addition. One thing we do want to be very careful of, when you use the relative abundance in this equation, it needs to be the percentage in decimal form. Okay, so what I'm talking about is, instead of using the number 52.40, for example, I would want to use this number, 0.5240. Okay, if your relative abundances in percentage form add up to 100, we would want these, the decimal versions of those percentages, to add up to 1. Okay, all you're doing is just dividing each of these numbers by 100, or in other terms, you're bouncing the decimal place 2 places to the left. Okay, so bouncing the decimal place 2 places to the left here gives me 0.0140. Okay, that 0 is there for a reason, so I'm going to go ahead and include it. 0.2410 and 0.2210. If you want to go back and check to make sure that those add up to the number 1, then you can go ahead and do that, but they do. So let me go ahead and use these numbers. All right, 0.0140. I'm going to add together the same part here for the second row. Okay. It is going to take me a moment to enter this all into my calculator. You know, this is the truly exciting part of chemistry. Like I said, you don't technically have to use parentheses because multiplication will take place before addition in the order of operations. And your calculator does know order of operations. Okay. While I'm putting this in here, let's just talk about the number that we should be expecting. Okay. We should be expecting a number, right? We're trying to calculate the average mass, or the average atomic mass. We should be expecting a number that is somewhere in this range, right? If you have a room full of people, the average height of those people cannot be less than the shortest person or taller than the tallest person, right? The average has to be somewhere in the middle, and that is the case for average atomic masses as well. So if we do not get a number that is somewhere in the middle, that is an issue. Oh, look, and it appears as if I may have done some sort of math incorrectly. I'm going to go through and double check all the portions of my calculation here. You know, let's just go ahead and be safe here, and let's put the parentheses in just for some extra caution. Not that it should change anything, but it might help me notice where I've gone wrong. Oh, here we go. This is where I went wrong. I entered in 22.10. Okay, that needs to be 0.2210. Oh, wait a second. Goodness gracious. 0.2210. There we go. All right, and would you look at that? Okay, we are actually getting an answer that makes sense. 207.216888888. Okay, so let me go ahead and write that down. Let's take just a brief moment to consider the number of significant figures. Now, you know, this is one of the reasons why I'm not a huge fan of significant figures, okay? Because here are mass numbers. We have lots of significant digits, right? Looks like the smallest number that we have is 6 with this number here. These relative abundances, this number only has 3. So technically we would be turning this whole number here into just 207. Sorry, let me show you that. 207. I'm not a huge fan of that. Okay, so I guess technically following significant figures this would be 207. Let's just add a few more here just to be, you know, a little bit careful. Let's just say that 207.22. Okay. If we go, so that is the average atomic mass, all right? If we go and consult the periodic table one more time, 207.2, that looks a whole lot like lead. Okay, so we have identified the element as well. And I can put the unit there, U, as the atomic mass unit for that, or unit for that that number there. Okay, so that's kind of a long process. Good news is I'm not going to go through all of the steps there for these next two problems. Okay, I'm going to let you guys. I'm going to assume that you guys can figure a lot of this out on your own. So let me pull back the slides and show you guys the next problem. Okay. A mass spectrometer was used to collect data on an unknown sample of a pure element. The data collected is presented in the graph below. Calculate the average atomic mass and identify the element. So basically the same thing, except instead of giving us numerical data, we have graphical data. All right. What you're going to do is you're going to have to interpret the graph, basically make a table like I did, right, using the values that you pull out of this graph, and then go through the same type of calculation to get to the average atomic mass. Okay, this down here on the x-axis, it says m over z. Let's not get too hung up on the details right now of what that means. This is just the mass number, okay? And then over here on the y-axis, we actually have relative abundance, right? That's a term that we're familiar with now. So different people are going to get slightly different answers on this problem because everybody is going to interpret the graph slightly differently. Okay, so for this mass number of 90, to me this looks like it's maybe a bit higher than 50, maybe 51, 52%. Some people might have some difference in interpretation there, and that's okay. 91 is, say, 12 or 13%, so on and so forth, okay? Now, you know, I don't think it makes a whole lot of sense to get any more specific than saying 51 or 52. I don't really think, based on our scale here, going by tens, that you can do any better than saying 51 or 52. I don't think you could say 51 and a half, for example. And actually, if you recall, if you were in my class last year, for example, when we talked about measuring things using like a graduated cylinder or a ruler, if your scale goes by tens, then actually when you try to measure something or interpret something against that scale, you can only get as good as the next digit. Okay, so if we go by tens, we can actually only do as good as measuring by the ones place. Okay, so one other thing we can do with this graph, like I said, I'm not going to go through the entire calculation, is we can take a good guess at it. So my mass numbers are 90, 91, 92, 94, and 96. And the largest relative abundance, almost half of the the sample came back as having a mass, actually more than half of the sample came back as having a mass of 90. That means that the average atomic mass for this element is going to be somewhere between 90 and 96, and it's probably more heavily weighted towards the 90 end than it is to the 96 end. In fact, it is more heavily weighted towards the 96 end. You can see that, right? That's one of the great things about a graph, is that you can visually interpret the data, and this is showing us for sure that our average atomic mass is probably somewhere over here, around 91 or 92. So if I go ahead and look at my periodic table one more time, if I look for elements that are around 91 or 92, I have two potential options here: zirconium at 91.22 and niobium at 92.91. Right now I'm not confident enough to say which of these it would be, so once again it would be kind of like a 50-50. You would have to go through the calculations based on your data interpretation to get a more confident answer, okay? And because you're interpreting the data from the graph, you may not get exactly what we have here on the periodic table, right? Hopefully you do get one that is closer to one than the other, and in which case you can feel pretty good about your choice for identifying the element. Okay. And then the third example problem, this one is a little bit different than the last two. This shows us that we have a mass spectrometer that was used to analyze a sample of Br2 gas, so bromine gas, molecular bromine gas. The data collected is presented in the graph below. Explain the presence of each peak on the graph. Okay, well, first of all, on this graph, we don't have a whole lot of information. Like, for example, these scale or these axes are not labeled. We can make a good guess as to sort of what these mean. On the previous graph, the x-axis was mass number. Let's go ahead and assume that that is what the x-axis is here for this graph. And then on the y-axis, this is a bit more confusing, because if relative abundances are supposed to add up to 100, well, this one peak is already at 100, so it's a little bit confusing, but think of this y-axis as being something like a relative abundance. Okay, it shows how common these things were picked up on the detector when compared to each other. Okay, so the 160 peak here was the most picked up, or the most detected. These right here were about half as much as that, and then these down here were much less than either of those. So we are supposed to explain the presence of each peak on the graph. Okay, so we've been talking about isotopes. One website that's really cool is ptable.com. Okay, so the letter P, table.com. On this website, there are a couple of tabs up here at the top. I've already gone ahead and clicked on the isotopes tab. Let's go ahead and click on the element bromine. Okay, well, we have a lot of these boxes here. Okay, what this has done, what this website contains, is a bunch of information about the different isotopes of elements. Okay, and this website shows us all of the different theoretical and real isotopes of an element. Okay, these different borders, okay, so like red, purple, black, blue, etc., are summarized here. Okay, I'm not going to get into all the details of this right now. I think at some point we will talk about some of this. What we're interested in right now are the black boxes, the stable isotopes. These isotopes are the ones that really do exist in the real world. Some of these other isotopes can be artificially produced, but as you can see here, they decay, or they emit a particle which causes them to decay, and they don't stay around for forever. Okay, so the black ones are the naturally occurring, like real isotopes of the element. Bromine only has two. Okay, there are these two right here, mass number 79 and mass number 81. If you click on the isotope, at least for bromine, it pulls up a page here. This is actually from Wikipedia, and on the side here there is a bit of a simplified tabulation of the isotopes of bromine. As you can see here, there are only two. Interesting thing about the isotopes of bromine, the two different versions are split about 50-50 in terms of abundance. 79 is slightly more common than 81, but it's about the same abundance. Okay, it's about 50-50. Keep that in mind, right? They're about 50-50, right? Mass number 79, mass number 81, it's about 50-50. Okay, if I go back to this graph, okay, take a look here, okay, mass number 79, mass number 81, both with approximately the same height, okay? Now this mass spectrometer, or this mass spectroscopy data, is supposed to be on a sample of Br2, so 2 bromines put together. It appears as some of this sample was going through the mass spectrometer, some of the molecules of Br2 split apart, and the detector actually detected individual bromine atoms, not as much as what we're about to experience over here. These are the actual Br2 molecules, but it does appear that it did pick up some just regular atomic bromine, okay, and they do come in like a evenly split package between the 79 and 81. Now what is more common, okay, according to the heights of these peaks, is the actual molecular bromine, okay, 2 bromines. If you take 79 plus 79, you get 158. That's where this first peak comes from. If you do 81 plus 81, you get 162. That's where this third peak comes from. If you do 79 plus 81, you get this peak right here, the 160 peak. The reason that this middle peak is twice as high as these others has to do with some probability, okay? If you were to take a handful of Br2 molecules, let's say you took 4 of them, for example, the probability, because bromine is basically a 50-50 split between 79 and 81, those mass numbers, the probability states that about a quarter of the time you're going to get 2 Br79s, okay, and that would give you an overall mass of 158 for that molecule. About another quarter of the time, both of those bromines are going to be Br81, and so you would have an overall mass of 162, 81 plus 81. About half the time, either the first one is going to be 79 and the second one is 81, or the first one is 81 and the second one is 79, and so in both of those cases, the mass comes out to be 160. That's why that middle peak is twice as high as these other 2. So, this question, explain the presence of each peak on the graph, your answer would not be a calculation or anything like that. It would be an explanation. It would just be you talking about why you think each of these peaks exist, right? These first 2 peaks come from just, atomic bromine. It's about 50-50 because the isotopes of bromine exist in a roughly 50-50 relative abundance. And then we just went through an explanation of why these peaks are the way that they are. Okay. Now this only says the presence of each peak, not necessarily the relative height. So it could be a little bit simpler than that. But there you go. Okay, so this is a pretty tough problem. Okay, and obviously you would need some additional resources if you only had this problem and you only had this graph. Without that periodic table, or without that ptable.com and all that information about the isotopes, you wouldn't really be able to answer this one very well, right? So I don't think there's a problem quite like this in your homework. I just wanted to show you this so you had a little bit of exposure to it, okay? All right, well, that's it for the video. This one is also shorter than the first one that I gave you, so yay for that. And I'll see you guys in class on Tuesday. Thanks.